All right, guys. So here we have chapter 18. And in this chapter, we will look at kinetic theory of gases. So here we're going to be looking at how we can describe the microscopic world of the atoms and molecules and using pretty much some of the statistical tools to describe things like temperature, for example, and pressure and all of those things. So here we have like a unit of this chapter. So we're going to look at the ideal gas law and the molecular interpretation of temperature. That means I'm going to show you uh, more like scientific view of the temperature, not necessarily like a coldness or hotness, but what is the temperature? Like what does it depends on? How can we interpret, let's say temperature from the these are molecular interpretation, right? From the let's say molecules and atoms in our system, and we're going to look at then some of the statistical, real life interpretation of, let's say of your system, this microscopic, system. So we're going to look at sort of like a statistical distribution of molecular speeds, and then we're going to compare the real gases compared to the let's say ideal gases. What is the difference? And then we're going to look at the change of phase graph. We're also going to look at in terms of what is humidity and vapor pressure, partial pressure, dew point. Those things can be also um, described from the motion of the particles and temperatures and things like that. And again, in a way, one thing we're doing in this chapter is um, we're kind of comparing ideal gas law to the real gases. What are the differences and what are the things that we can um, ignore or neglect, and some of the things that we can't. And if you're talking about, let's say, real life applications, what are the things that you should take into account? So van der Waals equation of state give us a little bit different view of the, let's say, pressure volume in the system if you don't ignore some of those little things that, let's say, um, contributes to the maybe a little bit of, the differences between ideal gas law and real gas equations. Then we're going to look at mean free path and diffusion. So some of the units in this chapter. All right, so one thing we're going to do here is I'm going to show you the derivation of an equation for a temperature. And it requires to use some like statistical tools. That means we are considering a container with n number of molecules, and this n can be a very large number, right? So when you have a container with the gas, you can think of like there's like Avogadro number of molecules and so on and so forth. So it's an extremely large number of molecules. And you can see, right? So the first one here says you are considering a large number of molecules moving in a random direction with a variety of speeds. Okay. And also another assumption that we have to make is that molecules are far apart on average. I mean, they're very, very tiny. So the distance between them, even though it could be like millimeters for us, right? But it's very large for them compared to their size. And molecules obey laws of classical mechanics and interact only when colliding. That means we're going to look at in terms of when they're colliding with one another and when they're colliding with the container wall, right? Thus the collision that we can look at it in terms of like elastic collisions. And let's say because elastic collision, this type of collision, if you remember this is the momentum, mass times velocity. So elastic collision specifically is when your momentum is conserved. It means this is the momentum of the system before and after it's conserved. And then also the energy of your system before and after is conserved. So that's the, momentum is a vector, so I can put it like this. So those two conditions have to be satisfied for the perfectly elastic collision. But momentum of the system conserved and the energy of the system conserved. That means the kinetic energy of before and after collision is basically the same for those collisions. All right, so now in terms of then trying to derive this equation, right? So in terms of trying to derive this equation, think like this. So we're going to have a container with some n number of molecules. Okay, so here's what we have. So think like this. We have a container with n number of molecules. Now, what I'm going to do, I'm going to basically show you the derivation. Okay, let me show you here. All right, so let me give you the full derivation here. So think like this. So we have a container. So let's say here, select some kind of container. It's a three-dimensional container. All right, I'm try to make it a little bit prettier. There you go. So, and what we have here is that it's filled with molecules that are kind of moving around, and again, those are extremely tiny molecules. So, like, let's say mass of this, and particle. Let's say it can be a particle or it can be like the atom or a molecule, depending, like, let's say what we have. But let's say this guy here is a particle like this, and it's moving with some velocity. Well, actually, let's make it like this. So here's the velocity. Okay, and this is the initial velocity. So it is moving like this, and it's going to collide with the wall. It's going to collide with the wall. And what I have here is that the position, or like, let's say the position where it collides, well, it's a collision with the wall. And what we'll get here is there's going to be a force acting from the wall in this direction. Okay, there's a force acting in that direction. And then one thing I can do here is I can see that afterwards, the particle then will be moving in this direction. So let's say this is V final. Now, breaking down this velocity into then, let's say, horizontal component, right? I can see that there is a change in velocity, which means there is a change in momentum. So using this, the momentum impulse theorem, I can say that the force, there was a force acting on it. Remember, force equals dp dt, right? So this is basically the force changing the momentum of the object. Then one thing I can do here is I can say that this is, I can do it in terms of delta p delta t, and this is equals to delta mv delta t. So this is basically in terms of change in momentum. Remember, there's a delta p is the change in momentum, which is m times v final minus m times v initial. Now, one thing we can see here is because v initial is to the left, and assuming that the speed exactly the same before and after, but the direction is not, so it pretty much going to be end up m times v final plus m times v initial, right? So basically, they have the same speed before and after, and the negative cancels out, becomes positive because the direction is opposite, after the collision. So you pretty much can say that m final equals m initial equals just m, sorry, that this is for the v. So v final equals v initial equals some v. So this becomes just 2 times m times v, and m naught is the mass of the particle. Okay, so we can put it a negative there, indicating this is in the negative direction. But the idea here is you just have 2 mv. Okay, that means when you have the force acting, right? Force on the molecule or on the particle, then what we have here is if I move this like delta t over here, right? Remember, this was the impulse, the product of F times delta t. This was impulse. So then I can say that when this force is acting, then I have 2 times mv over delta t, taking, again, change in momentum, right, to be 2 times mv. And, I can, carry the negative here, indicating that, there was a change in direction. All right, so then what I have here is this delta t represents the time. Let's say if I take this to be d, right, the distance, let's say if it starts from one end, goes, hits this, come back to the other side. So let's say that's sort of like a time for another collision. So then the delta t is a distance over the velocity, using this equation where the speed is equal to distance over time. So v is equal to distance over time, rearranging, then time is equal to distance over v. So now my distance here is then 2d, 2 times d, because, in terms of 1d and then a second d, back and forth until it collides. So 2d divided by velocity. And remember, so I'm pretty much considering the horizontal velocity. So I'm looking at just a one dimensional, right? So let's say it goes from here to there. So like, let's say all along the horizontal axis. Okay. That means what I can do here is I can replace the delta t right there with 2d over vx. Okay. So that means, then the force is equals to, then I have 2 times m vx over, so then delta t is then replaced with 2d over vx. So then I end up 2 mass times vx squared divided by 2d. So then this 2 can cancel out. And then I have negative m naught vx squared over d. So let's take this equation and assume, let's say right now we have that after we replace delta t, basically eliminate delta t. All right, so come back over here. I want to give myself more room. Negative mass times velocity x squared divided by d. Now, what I have here is, I can see that from here, this is the equation for just one particle. Okay. Now, I can see that also from the, let's say, the collision with the wall, the force is in the opposite direction. So technically the force is also negative. So those negatives in a way can cancel out. That means, my equation is force equals mass times velocity in x direction squared divided by d. So this is for sort of like, let's say, one particle. Okay. So this is the force that wall exerts on one particle. Well, we can take this and generalize it, right? So we have sort of like, let's say, n number of particles. So then what we can do here is we can look at in terms of the average force. Average force is, in terms of all the collisions, right, that in the wall that can exert to all the other particles. That means we can say that, all right, so then average force is equals to, then this will be in terms of the sum. We can say that the first particle and second particle, same third one, right? And then just, the average technically is, let's say force one plus force two plus that force, your ith particle, right? And then divided by n, which is number of particles. So in a way, this is kind of what we, what we have for this. Now, that means the average is just basically sum of your particles when I equals 1 to all the way to n, m naught vx squared divided by d. Okay. So then from here, I can say that mass, every single particle has the same mass. Distance is the same for all the particles, right? M over d can come out, then you have sum of vx squared. So basically you have something like this where this I equals 1 to n. So this is sort of like the equation that we can see from here. All right, so now what I have here is, if I'm actually doing this, I'm looking at the sum when I have to put a subscript over there, which means this is, I particle, right? When I equals 1, when I equals 2, when I equals 3, and this is for the, for all of them all the way to, n number of particles. Okay. Then here's what I can do. So this is Vxi, right? This is Vxi, well, Vxi square. One thing I can do here is this. So if I'm adding them all together from I equals 1 to n, imagine like I take the velocity of the first particle in x direction square, then plus velocity of the second particle in x direction square, then I'm adding them all together, then dividing by n, which is number of particles that I have. So technically this is average velocity in the x direction. So this is average velocity in the x direction. That means on average, right, this is the velocity of all the particles combined together along the horizontal direction. If I rearrange this, cross multiply both sides by n, then I can say that this I equals 1 to n vxi square is same as n times vx square. They are equivalent, okay? So then when I go to my equation for the force, I'm gonna replace then this term with that. because they are again equivalent. But what I'm doing, I'm going from microscopic, quantity, whereas an individual velocity, right? Vxi is individual velocity, to a more macroscopic. Macroscopic, like sort of like a big picture, right? So this is all the number of molecules, and this is average velocity, not just one, but all the particles combined together. That means my equation for the force then will be mass over distance, but then number of particles times Vx, so there's a square over there, there's a square over here, so V average x squared. Okay, so that means what I'm doing here is I'm starting with the microscopic, let's say, quantities, like mass of individual particle, the velocity of individual particle, and I'm slowly changing it into more of like a macroscopic quantities. N is a macroscopic quantity, right? Technically the force on the other side is also because I went from the the force on a single particle, where this is what I have, right, to a more like an average. Okay, so this is average is basically macroscopic. Now, going from this equation, one thing I can do here is this. I can generalize it even more. I can say, all right, so this is along the only, x-axis, right? So technically, the Vx is my horizontal velocity. But what I can also have here is, well, there is this velocity, right? That means every particle, I is the ith particle, right? Every particle can technically be moving, I don't know, three-dimensional, like one-dimensional, two-dimensional, but it can also be moving like as a three-dimensional, right? X, Y, Z. That means this square, right? Vi square is, or this quantity here, right? Vxi square that I had is only the one of the components of the velocity of that particle. It means Vi square, that means velocity of the ith particle square, is combination of its horizontal velocity square plus its vertical velocity square and plus its, z velocity square, right? That means, this is more complete picture of the motion of the particle. All right, so then if I'm going and looking at the average velocity square of all the particles, well, that can also be generalized like this. And again, you can say that average velocity squared is equals to all the horizontal velocities, average all the horizontal velocities combined, plus average of all the vertical velocities combined, plus average of all the z direction velocities combined. Okay, so have a little more, a complete picture. Okay. Now, one thing we can do here is, maybe like a relatively, let's say, assumption, right? So we make an assumption, but it's a, assumption that technically can be made in this type of case, where we can say that all the speeds are the same, regardless in which direction. That means Vx technically same as Vy, technically same as Vz. That means all of those velocities or the speeds, right, are the same. So which means that these quantities are exactly the same. So I can say V average square in a way is 3 times of the same quantity. So let's take, that means, if those are all the same, so I can say that, Vx square plus Vy square plus Vz square is same as 3 times Vx square, Vx average square. Okay, because they're all, since Vy is also same as Vx, Vz also same as Vx, I can just say that V average square is equals to 3 times Vx square. Okay, which means what I can look at here is, see over here I have Vx. So if I divide both sides by 3, I can say that Vx average square is like 1/3 of the average total, third square. Okay. Again, more generalizing, right? So then I can say that F average is equals to particle, mass over distance, then n times, so then 1/3 of the V average square. Again, not necessarily, it's not horizontal vertical, but let's say it's the parent, total velocity vector. All right, so I have this. Then what I can also, remember here is this. force is pressure, sorry, pressure is force per area. So pressure is force per area. That means, yes, we can, I know that force is a macroscopic, quantity, but remember, so in order for us to look at this type of thermodynamics, systems, pressure is a little bit more useful quantity for us. That means one thing I can do here is, you see, if I divide both sides by the area, then on the left side, force over area is technically my pressure. So pressure is equals to, and if you have a container like this, right, when this is D, this is D, area is what? Area is just D squared. Okay. That means here on the right side, then I have M over D times N, 1/3 of the velocity average square, divided by then D squared. Okay. Well, if I combine all together, then I have this. I have 1/3 mass times number of molecules times the velocity average square, and this is divided by D cubed, because D and D squared together give me D cubed. Now, what is D cubed? Well, D cubed will be the volume of that container, because it's D, D, and another D right there. Okay, so that's basically my volume. That means finally you can see, right, it's basically shaping into the equation that we know. So pressure is equals to, so then I have 1/3, then mass times number of molecules times average velocity square divided by the volume. Okay. So this is kind of, what we're almost, we can see, right, we're getting closer and closer. Now, one thing I can also do here is just manipulation, right? So I'm going to multiply both sides by 1. But on the right side, that 1 is going to be 2/2. So that means it in no way changes, the structure of my, let's say equation. But what I end up here is this. So let's say if this 2 goes right there, so it becomes 2/3. And then I have mass times, I can even move out number of molecules and even volume. But here what I have is mass times velocity square, average velocity square. Then this 2, the second, this one goes here, becomes like that. Because if I rearrange it like this, you can already see what I have over there. It's basically mass times velocity square over 2, or 1/2 mv square. Hopefully you guys remember what 1/2 mv square is, right? It's basically kinetic energy. But let's kind of still look at what we have. So on the left side, I have the pressure, but I'm gonna, cross multiply where I move those things to the left. So then I have P times V over N. So P times V over N. And actually, let me move the, just V and keep the N over here. So PV equals, then what I have here is that, so I have 2/3 N, then I have this, mass times velocity average squared divided by 2. Okay, so this is my equation. And in a way, this is my final equation that I can derive from that, system that I had. Now, what is the significance of this equation? Well, it tells you what is PV from this molecular interpretation. It's 2/3 times number of molecules times m naught v squared over 2. Okay. Now, if I compare this to the equation where PV is equals to NKB times temperature, I can see that in a way what I have is, since PV is equal to 2/3 N times m naught V average square over 2 and NKB times T, that means I can say that those are also equal to one another. That means, 2/3 N m naught V average square over 2 is equal to N KB times T. From here, I can see that I can drop the N number of molecules. And then what I have here is combining those together in such way. So I have that mass times velocity average square over 2 is equals to 3/2 times KB times T. which is then the equation that tells you what the temperature technically is. Remember, 3/2 kb is nothing but a constant. This is just a constant. So this m naught v average square over 2 is then average kinetic, what we call translational kinetic energy of the system, which means this is all the kinetic energies per number of molecules that we have. So in a way, what we have is a way of seeing that temperature is nothing but another way of describing the kinetic energy of your system, average kinetic energy of your molecules. Okay, so that means what we have here is, this is more, accurate way of looking at the temperature. So more kinetic energy your molecules have, faster they're moving, which means that, higher the temperature in your system. Lower their kinetic energy, slower they're moving, or lower the temperature. That means temperature is directly then, proportional to the, the kinetic energy in your system, how fast they're moving, right? So that means, what we can do here is, so this is basically average, translational average kinetic energy of your molecules. Remember, still we're looking at in terms of average translational kinetic energy. And the reason I said translational, because we are more or less ignoring the, let's say, rotational kinetic energy, ignoring the vibrational kinetic energy and things like that. That means we are only looking at translational. That means, kinetic energy due to the, linear motion. Okay. So then let's look at this in terms of the total translational. Okay. That means this is now, because this average, remember, so this average is basically in terms of the total number of kinetic energy divided by number of molecules, which is basically the kinetic energy of particle 1, kinetic energy of particle 2, divided by n number of molecules. That means the total translational kinetic energy is equals to basically n times your average kinetic energy. Okay, n times your average kinetic energy. That means what I can say here is then this is, this is average kinetic energy. So TR, translational average kinetic energy. That means n times average kinetic energy is what is the total translational kinetic energy is, which means that it's 3/2 n kb times t. Okay. Now from here, then I can also say that since n times kb is also equals to n times r, then total translational kinetic energy can also be written as 3/2 n times r times t. So this is two ways we can write the total translational kinetic energy, but in any case, right? So what I have here is, let's say, it shows that kinetic energy is proportional to the temperature. Okay, so kinetic energy is proportional to the temperature, and it's the best way you can think of, like, the temperature. Obviously, the hotness, coldness is not really a correct way of looking at the temperature, but temperature is interpretation of the molecular speed of your system. So that's why when the temperature is 0, which is absolute 0, it just means that your molecules are not moving. So that's why, remember, so if the absolute temperature in Kelvin is 0 Kelvin, so that this happens when the pressure equals 0. Why is the pressure equals 0? Because those molecules are not moving. They're not colliding with the container wall, so there is no pressure. So that's why you can see how everything kind of is nicely put together in terms of describing what the pressure is and describing how the pressure decreases with temperature, because temperature means that they're moving slower. Lowering temperature means that moving slower, and that is moving slower, pressure decreases, and then at some point they stop moving, which means there's no collision with the container wall, which means then that a pressure is also equals 0. All right, so that's kind of what we have. And let's go back to the lecture. So this is pretty much what the several, few slides describe, but, I wanted to give you in terms of more in-depth look at all of those, equations. So why we have, let's say, 1/3, of number of moles m times, so number of molecules m times v squared over volume. How did we get the volume? And then how eventually we would end up with average kinetic energy, which is 1/2 m average square equals 3/2 kT. Okay, so which means that average kinetic energy is proportional to the temperature, because 3/2 k is just basically a constant. Okay, so that's why in a way that the temperature, you're going to see, plays a really important role, especially in the next few chapters when we look at like internal energy and things like that. Internal energy basically also completely depends on the temperature. Okay, so the average translational kinetic energy of the molecules in an ideal gas is directly proportional to the temperature of the gas. Okay, so those are the equations that we have. So you can see, right, so there are two versions of the total translational kinetic energy. So try to not to confuse the total translational kinetic energy with the average translational kinetic energy. There's a factor of n. So this is the average, and the total is n times that average. All right. So one of the things we have here is, if you then look at this, this equation over here, and in this equation there's a V average square, we can then, what we can do here is we can look at what we call root mean square speed, VRMS. And VRMS is thing like this. So take this quantity, which is already the square of the means, right? Square of the means. And we take the square root of that. Okay, so things like this. So VRMS is equals to square root of the V squared. So V average squared. Okay, so that's why it's root of the means squared. Okay, because that is VRMS. We can write it in terms of a little easier way of looking at the speed of different molecules and different atoms. So that means, one thing we can see here is that how fast they're moving depends on the temperature. That means what we have here is that if you have a temperature, I don't know, let's say 300 Kelvin, for example, then 300 Kelvin means that every single, let's say, atom has exactly same kinetic energy. Every single atom has exactly the same kinetic energy. But how fast they will be moving, well, depends on what's the mass of that particle. Maybe it's a helium particle, maybe it's a hydrogen particle, maybe it's oxygen. Well, they all have different mass. They're all going to have the same kinetic energy, but they're all going to have different mass. And with a different mass, then we can look at in terms of their their speed, right, at that particular temperature. So as I say, right, if you have 300 Kelvin, means that you have the same temperature for all the particles, which give them exactly the same kinetic energy, because kinetic energy depends on the temperature. They all have the same kinetic energy. But how fast each particle or each type of element is moving depends on their mass. All right, so that's why looking at the RMS values, we can rearrange this, right? Rearrange this in terms of, so basically, taking this 1/2 mv average square equals, for example, 3/2 kb nt. So if kind of like, rearrange, so cancels 1/2, and then say v average square is equals to 3 n kbt over the mass, and then take the square root of both sides. Okay, take the square root of both sides. But the square root of this on the left side, square root of v average square, is then what we call RMS speed. Okay, so that's why we have two equations for RMS speed, one using that equation, and another one is in a way using this equation, but we changed that when let me show you here. So remember, so we have, it ended up being like this. RMS is equals to square root of 3 nRT over the mass But number of moles is then, remember, mass over molar mass. So I can technically have either this equation, or if I replace molar mass with total mass over molar mass, this total mass cancels out. So then we end up with just that, only in terms of the molar mass, which is sometimes like easier to, to calculate, right? So maybe because if you know what type of, let's say element you have, it's much easier to get the molar mass of that uh, instead of, let's say, how much you have, right? Because molar mass is the same, no matter if you have 5 moles, 10 moles, 100 moles, right? But, total mass is depends on how much specifically you have in that particular problem. So that's why this is probably much useful equation, because, R is a constant and molar mass is a constant, right? If you have, let's say, neon, this is the molar mass, regardless how much of it you have, okay? And you can calculate what is the RMS speed of that. Okay, and you can see, right, here's the RMS speed for difference. So you can see, right, you have hydrogen, 1902 meter per second at 20 degrees Celsius. Helium, 1352 meter per second at 20 degrees Celsius. Well, you have water, right, H2O. Now you have 637. Neon, 602. You have then a nitrogen molecule, or a carbon dioxide, uh, you know, uh, and you have the 511, right? So what you have here is, you can see, right, more heavier the element, slower it is moving. So you can see, right, as you go heavier and heavier, slower the speed. And you can see, right, directly that comes from the molar mass. So the smaller the molar mass, faster the speed. So that's why generally what we have here is, you can't really find any hydrogen or helium in our atmosphere, because they are moving really fast, too fast for our gravity to keep them in the atmosphere, and they can easily escape. So that's why hydrogen and helium you cannot find in our atmosphere. And for a very long time, scientists didn't know about helium. And the first time they actually discovered helium was in the atmosphere of the sun. And for them, it was some kind of exotic, let's say, element. And they, since the first time they found it in the atmosphere of the sun, they named it helium. Helium is, after the sun's name, Helios, right? So the Helios, the sun. So they found it there first time. So that's why the name is helium. All right. So let's look at then some examples where we can see how we can calculate those, RMS values, let's say. Here we have a flask contains a mixture of neon, krypton, and radon gases. So we want to compare their average kinetic energies of the 3 types of atoms. So you have 3 types of atoms, right, in a mixture. We want to see what is the difference between their kinetic energy. Okay. We're assuming that they have the same temperature. Okay. And then the root means, square speeds. All right, so now what we have here is basically, let's say, okay, you have neon, krypton, and radon. So let's say I think I have the neon in the table that I just gave you, but there's a more complete table where you can find, the values of all the molar masses and things like that for all of them. So, but in any case, so we have VRMS is equals to square root of 3 RT over molar mass, right? So that's kind of what we have. So let's say we have then the molar mass for the neon, and this is equals to 20.180 gram per mole. And molar mass of radon is equals to 222 gram per mole. And the molar mass of the krypton is equals to 83.80 gram per mole. Okay. All right, so hopefully by just looking at this, you should be able to see that the radon is the heaviest, right? And neon is the lightest from here, from this, this mixture that we have. Okay, so let's say taking this to be, our initial, let's say, values, and we're assuming that, let's say, the temperature of the mixture is such that, all those elements have exactly the same temperature. Now, A says, what is the average kinetic energies of these three types of atoms? Well, one thing we have is this. So the average kinetic energy, remember, is equals to 3/2 kb times t, right? 3/2 kb times t. I like to write b right next to the k, so that you know it's a Boltzmann constant, not a spring constant or the other things that we use the k for. This is the Boltzmann constant. So average kinetic energy 3/2 kb times t. Well, which means that, see on the right side, if I have, then this is like, let's say neon or a krypton or radon, right? Doesn't really matter. They all have the same kinetic energy. That means kinetic energy of the neon is the same as the kinetic energy of the radon, same as kinetic energy of the krypton. Why? Because they have exactly the same temperature. And that means they all have exactly the same kinetic energy regardless. So that's for part A. Part B then says, all right, so what are their root mean square speeds? Okay. And what we can do here is we can sort of like, let's say, calculate each one. What are the speeds, let's say. But then we can also do this. We can do a ratio. So I can say that VRMS for one of them, so let's say neon, over the VRMS for the krypton. Okay. So because what I have here is this. So that means this is going to be then square root of 3RT over M neon, then over 3RT over molar mass of the krypton. Okay. Well, I can see them from here. This can all cancel out. And all I end up with is then square root of molar mass of the krypton over molar mass of the neon. Okay. So then I can then just put in a ratio where the molar mass of the krypton is 83.80. You can see, right? That's a ratio, so even units cancel out. Gram per mole over 20.180 gram per mole. Units cancel out, and we get just a number, 2.04. But this number tells me that VRMS of neon is equals to 2.04 of the krypton, the VRMS of the krypton. That means it is moving twice as fast. So it is moving twice as fast. So if, for example, I go back to this table, I can see that I have for the neon, which is 602 meter per second, 12, let's say at 20 degrees Celsius room temperature. Then I can say that then the krypton will be moving about half of that. So probably about 300 meter per second. All right, so then the same thing I can do for all of them. Right, so that means I can say that VRMS of neon, for example, over VRMS for a radon, and this will be then square root of, again, the ratio of their molar mass, right? So it will be then 222 divided by 20.18, and so this will give me then 3.32. That means it's going to be 3.32 times faster than the radon. That means radon will be about 3.32 times slower. But that means, a little over 1/3 of the 600. So maybe around 200, maybe 180 meter per second. And then we can also do in terms of VRMS of krypton over VRMS of the radon. So then this will be 222 over 83.8. So then we get 1.6. That means, again, what we have is that, the krypton is moving about 1.6 times faster compared to radon. Okay. So then what we have here is, then you can see, right? So those are, like, let's say the ratios we can use to figure out in terms of what are the speeds. Okay. So, all right. So hopefully, again, those are the things that you should not try to remember. Everything will be given to you or in the table, right? So, but you can see, right, it's easier to get it from those quantities. Here's another example. I have a deuterium, which is an isotope of a hydrogen, okay, right? It's a nucleus of a hydrogen isotope and consists of one proton and one neutron. The plasma of deuteriums in a nuclear fusion reactor must be heated to about 300 million Kelvin. What is the RMS speed of the deuteriums? Is this a significant fraction of the speed of the light, where the speed of light is 3 times 10 to the 8 meter per second? There should be no square over there, sorry. All right, so now what I have here is I'm told that I'm dealing with the nucleus of this hydrogen isotope, and it has one proton and one neutron. Okay, which means that I can find my total mass by taking mass of the proton plus mass of the neutron. Okay, so the mass of the proton is 1.67 times 10 to the negative 27 kilogram. Again, those are available in tables. Plus mass of the proton is, sorry, neutron is very identical to the proton, but it's slightly heavier. So this is 3 and this is 6.5, times 10 to the negative 27 kilograms. So combined together, that means I can say that the mass of this nucleus is 3.35 times 10 to the negative 27 kilograms. So we got the mass, okay? Because then I can say then VRMS is equals to square root of, remember there was an equation with where we can use the mass, right? So the equation where it was in terms of 3/2, sorry, actually half cancel out. So 3 times n, sorry, 3 kBt over then the mass, like this. So then I can use this, I can say it's a 3 times, and here's Boltzmann constant value. It's 1.38 times 10 to the negative 23. So joules per molecules Kelvin, and times the temperature. So this has to be an absolute value. Well, sorry, not absolute value. I mean the Kelvin scale. So 300 million Kelvin, we already given in Kelvin. So that means we just write that as 300 times 10 to the 6 Kelvin. That's a 300 million Kelvin. And divided by the total mass, 3.35 times 10 to the negative 27 kilograms. And I can say then VRMS is equals to, once I calculate that, 1.93 times 10 to the 6 meter per second. Okay. Now it says, what is the significant fraction of the speed of light? Well, I can do a ratio, right? I can do a ratio because, I know what the speed of light is, but you can already see, right? It's not necessarily a significant, let's say, difference. So if I do then VRMS over C, so 3 times 10 to the 8 meter per second, so I get 6.43 times 10 to the negative 3. So not quite, right? It's just let's say like a fraction, right? So almost 1,000 times, over 1,000 times, like let's say 6,000 times less, speed compared to the speed of light. All right. Part B says, what would the temperature of the plasma be if the deuteriums had an RMS speed of equal to 0.10 C? Okay. So that means, for example, then the idea here is that in terms of, like, let's say, as you increase the temperature, the faster they're moving. So we had 300 million Kelvin. So, but if I continue increasing temperature of the plasma, it's, the molecules, going to start moving faster. So then the idea is that how much should I have to increase? So then speed is equals to 0.10 C. Well, in that case, what I have here is I'm using this equation, 1/2 mass times speed square equals to then 3/2 times K times T, KB times T. So I'm using this equation, then I can solve for the temperature. So I can say then temperature is equals to, canceling those, becomes m times speed square divided by 3 KB. Okay, so then I can calculate that. Again, this is, being RMS speed right now. So I can say that this to so let's see. So the mass, 3.35 times 10 to the negative 27 kilograms. Then 3 times 1.381 times 10 to the negative 23. That's for the Boltzmann constant. Then I do the RMS speed, which is 0.10 c, which means that, take the speed of light divided by 10, basically. So 3 times 10 to the 7 instead of 10 to the 8. Okay. So if we calculate, we can see that temperature is 7.3 times 10 to the 10 Kelvin. Okay. So, which means that roughly, I think 73 billion, right? Billion Kelvin. So we have to increase it, what is it, like, 30 times almost, in order to reach the, the speed of 0.1 C. All right, so one more example here. 2 mole sample of oxygen gas is confined to a 5-liter vessel at the pressure of 8 atm. Find the average translational kinetic energy of the oxygen molecule under these conditions. All right, so we're given a number of moles, and then we're given the volume, and then we're given the pressure. Okay, and what we want to do is we want to find average translational kinetic energy of the oxygen molecules. Now, what we have here is, if you remember, right? So then we had the PV that was equals to 2/3 N times, then we had that as M naught V average square over 2, right? So that was the equation that I showed you. So we have this equation where basically here in the parentheses, this is the average kinetic translational energy. Okay, so let me put like TR for the translational kinetic energy. That means in a way my equation is PV equals 2/3 N times average translational kinetic energy. Okay, so that means if I rearrange, then average translational kinetic energy would be then 3/2 PV over N. Okay, so now N is the total number of molecules, but I'm given in terms of the, let's say, the number of moles. But remember, they're related, right? So the total number of molecules is the Avogadro number of molecules times the number of moles. That means I can just say it's 3 PV over 2 times Avogadro number times number of moles. Okay, and in a way, I have everything that I need at this point to calculate it. That means I can say that translational kinetic energy is equals to, then this is 3, then pressure is 8 atm, but I need to convert it into Pascal. So where 1 atm is 1.013 times 10 to the 5 Pascal, then times the volume, which is 5.00 liters, which is then 1 liter is 10 to the negative 3 cubic meters, and then divided by 2 times Avogadro number, which is 6.02 times 10 to the 23. So the molecules per mole, and times the number of moles, which is 2 moles. All right, so doing this, we can see, right, so that ATM cancels out, liters cancels out, number of moles cancels out. So, and what we have here is, if I do this calculation for the translational kinetic energy, then we will have 5 point, we can do like this. So 5.05 times 10 to the negative 21 joules. There you go. So that's the translational kinetic energy for those oxygen molecules.